The Higgs field, the universe's quiet setting dial, expanded. To understand how reality could reset, start with a field you never feel. The Higgs isn't a particle you bump into. It's a field that fills all of space. Particles move through it the way swimmers push through water, and their resistance, how strongly they couple, shows up as mass. Turn the Higgs field down and the electron gets lighter. Turn it off and the weak force merges back with electromagnetism, chemistry collapses, and stars as we know them don't happen. The Higgs is a quiet dial that decides whether matter behaves like matter. A better everyday picture. The Higgs is the thickness setting of the universe. Imagine walking through a room filled with invisible fog. Neutrinos are sprinters wearing aerodynamic suits. They barely notice the fog. W and Z bosons are in full winter coats. They plow, slow, and feel heavy. The parameter that sets how thick that fog is, the vacuum expectation value, VeV, around 246 GeV, decides the roster of masses, from electrons to top quarks. Now, fields don't sit flat. They live on energy landscapes. The simplest picture looks like a bowl, but the Higgs potential, the one that matches our world, looks more like a ringed valley with a hill in the middle, the famous Mexican hat. The young universe cooled, the Higgs rolled off the hill and settled into the valley, giving particles mass. That's electroweak symmetry breaking. But here's the catch. Not every valley is final. Some are local lows with a deeper floor hidden beyond a ridge. If the Higgs sits in a local minimum, a false vacuum, it's stable against small nudges, but not guaranteed forever. Quantum mechanics allows tunneling. The field can borrow a path through the barrier, landing in the deeper valley without climbing the ridge. Why does anyone think our valley might be false? Because the Higgs self-coupling, the quartic term that shapes the valley, doesn't stay constant when you probe higher energies. Renormalization tells us couplings run. Feed in measured values at lab scales and evolve them upward, and the Higgs quartic can drift towards zero and even negative at high scales. Negative quartic is a red flag. The brim of the valley tilts down somewhere far above our everyday world. That's metastability. It doesn't mean we slide today. It means, in principle, a deeper valley exists. This is where the top quark throws its weight around. The top is heavy and couples strongly to the Higgs. Its mass and the strong coupling, alpha ears, feeds into the running of the Higgs quartic. A slightly heavier top pulls the quartic down faster. A lighter top eases the tilt. The Higgs boson mass, around 125 GeV, anchors the starting point. Put these together and you can draw a phase map. Regions where the electroweak vacuum is absolutely stable. Regions where it's metastable with lifetimes far beyond the age of the universe. And regions where it would be outright unstable. Our best fit ellipse, Higgs B, 125 GeV, top Sorority 4 on 173 GeV, lands near the border in the metastable zone with error bars. Straddling the line near the border does a lot of work here. It means the precise definition of the top mass matters. A Monte Carlo mass versus a short distance mass shifts the answer. It means higher order loops, threshold corrections, and how you match measured observables to running couplings matter. Teams keep pushing precision. Multi-loop RG running, careful matching at the top mass scale, resumations. The direction remains consistent. Absolute stability is disfavored, but not excluded. Metastability is favored, with the vacuum lifetime absurdly longer than the current cosmic age. 2024/2025 tighten the screws. Global fits now fold in, refined top quark mass combinations that translate Monte Carlo masses into short-distance schemes with smaller systematics. Improved alpha TARS inputs from lattice QCD and event shape analyses, shaving uncertainties that used to blur the phase boundary. Higher loop beta functions and threshold matching for the Higgs quartic and top Yukawa that stabilize the RG flow compared to 2010's era fits. Net effect, the metastable but safe region still wins. The stability line nudges slightly, but the verdict holds. Our vacuum, given current inputs, is either truly stable or comfortably metastable with lifetimes that dwarf black hole evaporation timelines. The error bars shrank. The panic did not grow. If metastable, what does the landscape imply? A vacuum decay proceeds by bubble nucleation, an Einstein-driven event in the field's Euclidean picture. a tiny bubble of true vacuum appears. Most are too small. Surface tension collapses them. But if a fluctuation kicks a bubble over a critical size, interior energy wins. The wall becomes a front that accelerates to near light speed, converting false vacuum to true as it goes. Inside, the Higgs vacuum expectation value could shift dramatically. Particle masses and force strengths would change. Bound states relying on today's parameters wouldn't survive. There's no fireball, just new rules, instantly local wherever the front arrives. You don't see it coming, there's no precursor we detect, and no time to react. Analogy time. Picture your desktop icons reskinning mid-click. The files aren't deleted. They were never files to begin with. They're representations. The bubble wall is the OS update you didn't approve that replaces the icon set and the file system format in the same instant. Your old shortcuts don't map. The new system may have its own files, but nothing crosses the translation layer. That picture sounds cinematic, but the rate is governed by an exponential, XP minus S bounce / haircut. The bounce action is huge if the barrier is tall and wide, which pushes the decay probability per volume per time to near zero on any human or stellar timescale. That's why metastable doesn't mean imminent. Integrate that tiny rate over cosmic volumes and ages, and we still get lifetimes that dwarf black hole evaporation. Our universe has been stress tested by ultra-high energy cosmic rays with center of mass energies beyond anything in colliders, and nothing flipped. Safety studies lean on that. If nature hasn't triggered decay in 1 billion years of higher energy impacts across the cosmos, our machines aren't the red button. One more precision note for the nerds keeping score. The top mass in short-distance schemes trends a bit lower than naive MC reads, nudging the cortex running slightly upward, safer. The Higgs mass world average remains near 125.25 GeV with small uncertainties. Shifting it up would favor stability, down would favor metastability. Alpha's improvements modestly tighten contours. No recent move has shoved us into outright instability. So the Higgs field acts like a universal setting dial, and its potential hints at a second, deeper setting we'll never visit unless quantum tunneling cheats the ridge. Our measurements put us near the knife edge, where the story could have gone either way. For scientists, that's a clue. Either we got cosmically lucky, or new physics stabilizes the potential at high scales. For the rest of us, it's a lesson in confidence with error bars. The ground beneath our feet is steady enough to build on, and weird enough to keep measuring. Metastability 101, living in a temporary minimum. Metastable sounds exotic, but you've seen it. Think supercooled water in a clean bottle. It looks calm below freezing because tiny ice crystals haven't had a place to start. Tap the bottle, and in seconds the whole thing flashes to slush. Nothing about the water changed, just a small seed crossed the threshold and the phase it should prefer took over. A false vacuum is the cosmic version of that quiet tension. We're settled for now because the barrier holds. That doesn't mean there's no deeper state. It means the path to it isn't open by ordinary motion. In quantum mechanics, barriers aren't brick walls, they're probabilities. A particle stuck in a valley doesn't need enough energy to climb the ridge, it can tunnel. Fields can, too. The formal story uses a trick. Rotate to imaginary time, find a special solution called the bounce, and compute its action. Translate back, and you get a physical picture. Every so often, a tiny patch of space fluctuates into the lower energy phase. Most patches are too small. Surface tension squeezes them out before they spread. But if one appears above a critical radius, volume energy wins. The interior wants to grow. The wall becomes a front. That front is not a fireball. It's a moving boundary between two sets of constants. The speed limit is set by the field equations, and for a thin wall case, it races outward at nearly light speed. Ahead of it, everything is ordinary. At the wall, quantum fields transition. Behind it, the rules are different. Maybe slightly, maybe catastrophically. If the Higgs vacuum expectation value shifts down or up, particle masses shift with it. A proton's stability, an electron's weight, even the range of the weak force all redraw. Bound states that rely on today's delicate balances, atoms, molecules, stars, don't map cleanly into that new book. They unwrite. What could start a successful bubble? In the vacuum, pure quantum chance. The rate per unit volume per unit time looks like a prefactor multiplied by an exponential XP minus S bounce hair-free quarter. That action S-bounce is large when the barrier is tall and wide, which pushes the rate to absurdly tiny numbers. That's why a metastable universe can last longer than any star, any galaxy, any black hole. Thermal kicks can help in early hot epochs. Gravity can modify the calculus. The Coleman-DeLucia story shows how curvature shifts the bounce and changes the rate. Seed effects from defects or compact objects have been studied, with debates about whether they enhance or suppress decay. But in our cold, flat patch today, the plain vacuum channel dominates, and it's a miser. There's a second threshold that matters, the critical size. Below it, bubbles collapse because creating wall costs energy. Above it, the volume energy gain from moving to the lower vacuum outweighs the wall penalty. That balance makes the process all or nothing locally. You don't get a growing drizzle of true vacuum fog. You get a rare event that either snuffs itself out or takes the field with it. Crucially, there's no warning signature. The front outruns any information about itself. By the time a photon could tell you it's coming, the wall is already here, and your local definition of you doesn't exist. Could we trigger it? The fear is intuitive. Smash particles hard enough, maybe you poke the barrier. But nature has been smashing harder than we ever will. Ultra-high energy cosmic rays hit nuclei in our atmosphere with center of mass energies well beyond any collider. They've been doing it for billions of years across every galaxy, star, and dust grain. If those collisions made critical bubbles, the universe would have rewritten long ago. Safety analyses lean on that logic. Colliders reproduce tiny, fleeting states that occur routinely in nature, but in controlled abundance. We're not special enough to tug the vacuum. Vacuum mysteries, false vacuum and metastability expanded. Here's the deep cut behind the metaphors, the parts that keep theorists honest in 2024-2025. Precision inputs decide the label. The top quark mass, translated into a short-distance scheme, the Higgs mass, 125 GeV, and the strong coupling alpha 2 set the starting coordinates for the RG flow. Improved combinations from LHC, Tevatron, and lattice QCD narrow the ellipse on the stability map. The center still hugs metastable, with absolute stability allowed inside errors. Higher loop control matters. 5-loop gauge beta functions and 3 to 4 loop threshold matching reduced scheme dependence that used to blur conclusions. The cortex turn towards zero negative shows up later or earlier by tiny amounts. But the exponential in the tunneling rate makes tiny translate into still ludicrously long. Just sitter wrinkles. Our universe's late time acceleration, effectively a de Sitter bath, slightly modifies bounce calculus. Coleman, DeLucia corrections and discussions of finite temperature de Sitter fluctuations get attention, but for standard model parameters, the net effect doesn't drag lifetimes anywhere near danger on practical clocks. Seeds and catalysis. Tiny black holes, cosmic strings, or dense defects can, in specific models, tweak decay rates. Follow-ups routinely find mixed or suppressive effects, and the killer constraint remains. If catalysis were strong, the early universe, hotter, denser, seed-rich, would have flipped. It didn't. Existing as a data point. New physics as a dial. Add an extra scalar, singlet, triplet, or a supersymmetric spectrum, and the cortex running can bend upward, stabilizing the brim. Add heavy fermions with strong Yukawas, and you can pull it down. Precision bounds box these toys in. The vacuum story is a bookkeeping problem, and every new ledger entry shifts. Columns. Think of it like a Jenga tower with error bars. The known blocks, Higgs mass, top Yukawa, alpha W keep the tower upright. Each measurement you tighten adds a shim beneath a wobbly block. Each speculative new physics brick placed at the top can tilt the whole stack slightly. The 2024's 2025 adjustments didn't send pieces flying. They just made clear that even if we're on a ledge, the ledge runs far past any horizon we can use. So living in a stable minimum means living with a loophole that exists and almost never fires. The decay rate could be so small that not even the integrated history of the observable universe gets you a single event. And if the standard model survives to absurd scales, black holes will evaporate, and the cosmos will drift toward heat death long before vacuum decay becomes statistically likely. That's the tension. Real in principle, negligible in practice. Which leaves us with the question scientists actually argue about. How likely, given our measurements, is metastability the right label? To answer that, we need to look at how the math runs with energy and how precise inputs push the vacuum line. Bubble walls, The rewrite spreads at almost light speed. So what actually rides on that bubble wall? Not heat, not shrapnel, translation. The wall is a moving boundary in the Higgs field, and every standard model field ties into it. As the interface passes, the vacuum expectation value, the baseline that sets particle masses and interaction strengths, snaps to the new number. Wherever the wall has swept, the constants are updated. Wherever it hasn't, they aren't. There's no gradient you could feel, because feeling relies on the very interactions the wall is rewriting. Inside the bubble, reality runs a slightly different program, or a very different one depending on how the potential shifts. If the new Higgs value is lower, some particles get heavier or lighter. If it's radically altered, certain particles might not even be stable. Mass ratios that were finely tuned by evolution and stellar nucleosynthesis no longer line up. Electrons could be too heavy to bind to protons. Protons could become unstable. The weak force range could expand or shrink. Every bound state you've ever counted on, atoms, molecules, nuclei, relies on a balance of forces that the new vacuum does not promise to preserve. The wall itself is thin on everyday scales. In the thin wall limit, it's set by the microphysics of the potential barrier and surface tension. As it moves, it harvests the stored energy difference between vacua, and that energy goes into the fields at the front, into the wall structure, into excitations, possibly into a spray of new particle quanta permitted by the new rules. But don't picture a shock wave that blasts air. The medium is the fields. Air is just one victim among many, and it only exists on the false vacuum side. The speed is the part that kills warning. In flat space-time and simple models, the wall accelerates toward the speed of light. It can't outrun light inside its own region, but it stays close enough that no alert from ahead will ever beat it. Information about the bubble's approach travels at light speed through the false vacuum. The interface follows at essentially the same speed. Signals you would need to prepare simply can't arrive in time, and preparedness wouldn't mean anything after the transition anyway. What happens to matter caught by the wall? There isn't a dramatic push. Think of it as the rug being swapped under your feet while you stand. The fields you're made of are reparameterized. If atoms have no bound states in the new vacuum, the electron wave functions unbind. If nuclei become unstable, they decay into whatever the new spectrum prefers. If charge assignments or coupling hierarchies change, conservation laws you thought were absolute become bookkeeping in a different ledger. No chemical reaction runs, chemistry as a concept stops mapping to the new ground rules. Meanwhile, star interiors and black holes aren't special refuges. The wall doesn't need cold or vacuum. It needs the field to exist, which it does everywhere. The interface slices through plasmas, degenerate matter, and event horizons exteriors equally. Gravity curves the path, but it doesn't quarantine the rewrite. Even space-time curvature only modifies the local bounce conditions. Once a supercritical bubble exists, the expansion front is robust against medium details because it's driven by the vacuum energy difference, not by material drag. Could the wall stall? Only if the energy difference went to zero across a broad region, or if friction from particle production bled enough energy to halt it. Scenarios model builders examine, but the generic outcome still favors a relativistic front. If anything, particle production at the wall is a signature that would flood the new region with whatever the new vacuum allows. Quanta that quickly relax into that world's ground states. To us, that looks like annihilation. To hypothetical observers born under the new constants, it looks like initial conditions. And outside the bubble, there's no hint. Telescopes can't see its edge because light from the edge can't outrun the edge. There's no cosmic ray precursor, no gravitational wave howl that arrives early. The only way you know is to be rewritten, and that erases the knower. It's the cleanest catastrophe physics has ever offered. No suffering, no chance, no survivors, no memory, a reset that leaves not even a story behind. Why physicists take this seriously?